I'd like to start out by thanking Brian for putting together what looks to be a fascinating set of talks about deep water issues, and also thanking him for inviting me to come here to address you. Like Professor Haddad, I work across disciplines. I'm a geophysicist. I think he said he's a geochemist. That automatically means that we have to pull from various disciplines. Geophysicists mean geology and physics. But it extends even further than that now. I should say that one of my really fun students I work with is actually a student in computer science. He's a statistician. And we have a lot of fun trying to educate each other about our respective fields and how to apply what we know to problems related to earth science. There's been a lot of focus recently on energy, on the promise of natural gas. There's a lot of discussion about how hydraulic fracturing has revolutionized our ability to produce gas domestically. And it's had dramatic impact on both the projected supplies of natural gas as well as the price of natural gas. There's also a lot of discussion about the environmental impacts of that. Well, that goes on, and it's really been a revolution. There's still a tremendous amount of interest in what goes on in the Gulf of Mexico, and effort to extend our ability to both explore and drill for water and for oil and gas in increasingly deep water. So the focus of my talk is going to be not on land seismic or land geophysics, but on marine geophysics, and focused on the deep water Gulf of Mexico. This is just to help set the context. It shows a map of sites where oil is currently produced in the Gulf of Mexico. You can see there's a lot of locations there. The Deepwater Horizon is one of those dots. But even since then, people have been interested and are exploring in deep water and ultra deep water. This is a plot from the Energy and Information Agency showing production from the Gulf of Mexico, breaking it down by water depth. And you'll see they categorize water depth by water less than 1,000 meters or 3,000 feet, water going between a depth of 1 kilometer and 5 kilometers, and now even water at depths greater than 5 kilometers. To me, it's always been amazing, and we'll learn more about this later, that we can actually do operations at depths of greater than 5 kilometers. But you can see that the Gulf of Mexico is a major supplier of oil for the United States. It's producing on the order of 30% of the oil. But if you can look at this plot, you'll see that the production from the shallow water, which is shown in green, is declining. And that's why we're going to deeper and deeper water. We're also going to deeper and deeper water because we've had success. And part of that success has been because we've had improved ability to image the subsurface of the Earth using geophysics and to reduce the risk of drilling in deep water regions. Many companies are exploring in the Gulf, some of them domestic companies, some of them foreign companies. But this is a picture taken from a recent Wall Street Journal article just showing some of the recent finds in the Gulf of Mexico. And I don't know if you can see the companies such as Anadarko, Shell, Total is interested in the Gulf of Mexico, Hess, many companies that are having major finds in the Gulf of Mexico. You see, and we'll have, again, you'll find this more when we talk about drilling later. Drilling is not cheap. My guess is that these are probably lower bounds on drilling costs to drill a well in the Gulf of Mexico, $40 to $50 million. If a company's going to invest that kind of money, they want to have some idea that their investment is going to pay off. Once they drill the well, then they have to complete it, and that costs money. So what do we need to know before we drill a well? Well, of course, an investor wants to know if they're going to make money. But the question is, how do you make money? Well, you make money by finding oil. And as geologists and geophysicists, we want to try to tell people where to drill wells. And what we look for when we drill wells is traditionally we've looked for geologic structures that are similar to those where we found oil before. And we have a pretty good understanding in the Gulf of Mexico of what kind of structures we would like to find. A lot of them are associated with salt. Salt presents both a benefit and a problem because salt acts as a cap for reservoirs. that can be very productive, but it also is very hard to image through. Not only do we want to find structures that we think might have oil and gas, we want to find out if that structure has oil and gas. It may have fluids. And using geophysical techniques, we can tell if there are fluids, but then we want to know what the fluids are. Are they oil, gas, brine, mixtures of those? Furthermore, we want to know if there's a seal over the reservoir. If there's a reservoir and it looks promising, we think there's a lot of porosity in the reservoir, we have good reason to believe maybe there is petroleum in the reservoir. The question is how much. And whether there's, how much is there, is a function not only of the size of the reservoir, but how well it's capped. What's the seal of the reservoir? What's the seal? Are there faults in the reservoir that will cause a loss of fluids? These are things we'd like to know, and we want to know them at great depth. First of all, we've got to get through the water, and then we've got to get through overlying geologic structures. Furthermore, geophysicists are increasingly called upon to try to say something about drilling hazards, and one of them is overpressure. My understanding is Deepwater Horizon was not a failure to predict pressure at depth, but one of the things that we're asked to do is to try to tell before you've drilled a well, or as you're drilling a well, what is the pore pressure going to be ahead of the bit? Often you get regions of high pore pressure, and those can be dangerous if you're not ready to handle them when you encounter them. Other geological hazards we like to understand that include geomechanics are the fact that salt is mobile. And it's the mobility of the salt that created the reservoirs, but that mobility can cause drilling hazards also. So how do we explore for petroleum in deepwater regions? Well, we usually start out with seismic. And with all due respects to Brian, we usually do seismic. We use seismic. Occasionally we use electromagnetic. There's increased interest in using electromagnetic methods and in combining electromagnetic methods with seismic methods. We occasionally use gravity. Both gravity and electromagnetic are quite a bit cheaper methods to acquire data, but they're low resolution methods. We drill. Drilling, as I said, is expensive. It only allows us to sample a very small region of the subsurface. And we use experience. Interpreters who look at geophysical data have a lot of experience based on previous drilling to try to help infer what might be a good prospect for drilling. Basic seismic acquisition. I feel a little bit humble presenting this talk because I'm not quite sure what level to start at, but I'm going to start at a fairly basic level. And how do we image the Earth with seismology? It's similar to what we might do with acoustic ultrasound in the body. The problem we have with the Earth is that we can only view it from one side, and that's the top. So we use things like seismic reflection, and this is a very primitive early version of seismic reflection. We hit the ground with a hammer, create vibrations that propagate in the Earth, and they're reflected off the strata in the Earth's subsurface, and we record them at the surface, and then we try to provide an image of the Earth's subsurface. This is very similar to the method that was used by Mohorovičić in 1909 to discover the first major discontinuity in the subsurface that is of interest to most earth scientists, and that's the crust mantle boundary. But what we do now is we use much more sophisticated hammers. We use significantly more and better geophones, and we use advanced processing methods. The challenges we encounter in deep water imaging are similar to some of those we encounter in just imaging anywhere in the Earth. The big one is limited viewing angle. We can only look at the Earth from one direction. In medical imaging, you have the advantages that you can completely surround a patient with sources and receivers for imaging. We can only look from one direction. And that causes significant degradations in the quality of images we can get. And a lot of the work we've done over the last few years is try to find better ways to view the Earth at different angles. And I'll show some methods we use to do that. Another issue is seismic wave penetration. Seismic waves attenuate dramatically as they propagate in the Earth due to anelastic processes, which we'd like to understand. But it limits the wavelength that we can sense the Earth from, and that limits the spatial resolution that we get but because of the wavelength. Wavelengths typically, when you get to deep water, are generously on the order of 10 meters, probably longer. The Earth is a complex medium. Propagation velocities, you see, range over, say, a few tens of meters near the seafloor to several kilometers in salt. This creates a multi-scale problem that's a problem both for imaging and simulation. The salt itself is a huge problem because it has a large velocity contrast with surrounding sediments. That large velocity contrast deflects seismic waves and limits our ability to image beneath salt. So we try to find better ways to image beneath salt because that's where we want to go for reservoirs. Cost is a big issue. Just to drive home the point of how the complexity of the Earth influences our ability to image, this is a picture of a model structure that was developed for West Africa. And what I've drawn here are red lines showing the paths that rays would take if we, say, shine seismic waves through the medium. It shows how the paths would go. And so if you shine a beam of light, it doesn't go in a straight path. It's a very complex path. And what happens is, because of the medium, you often get a focusing of most of the rays in some small part of the region. And that means you have a defocusing of rays or seismic energy, if you're using wave field, from a large fraction of the region. You want to get some kind of uniform illumination of the region to try to say something about the spatial structure throughout the medium. And this creates problems. Salt is particularly bad at bending seismic rays. Other challenges to deep water imaging is we want to do it fast. There's a sale coming up next week. You need to know the answer. You need to present it to management and tell them where you think the best leases are they should bid on. Processing limitations, tremendous computing requirements, large volumes of data, several terabytes to several hundred terabytes of data are collected in a marine acquisition, and you have to process it. Environmental issues during acquisition, we're using active sources, explosions or air guns. These have impacts on the marine environment. Oil platforms, if there's an oil platform, we usually want to know what's going on, what the seismic structure is, or the geophysical structure is beneath the platform, but we can't run a ship over the platform, so we're limited in where we can drive a ship to acquire data. So imaging in a region that has a lot of platforms is a challenge. Another thing that we like to do, even after we've drilled wells and we start producing, is understand how the reservoir is changing with time. In seismology, in earth sciences, we call that 4D, and the fourth dimension is time. We acquire a successive series of images over time, maybe every 6 months, maybe every year, and try to infer what's going on in the subsurface by some kind of processing of those data to understand what's going on. A tremendous need for trained personnel. As an academic, I like to think that the students I train are going to get jobs. And I'm happy to say that in geophysics right now, if a good student, the job market is tremendous. But there is a real shortage of trained people. There's a tremendous pipeline of older people who are getting ready to retire and a need for early career geophysicists to replace them. What are the answers? Well, there are a lot of them, and I can't touch on all of them here. What I'm going to present is biased by my view, but one of the answers that's driven a lot of advances in our science is more data, smarter data, using different acquisition geometries, using better sources, better receivers, obviously improved processing algorithms, combining seismic data with other seismic analysis with other methods, and bigger computers. I should say, I think it used to be that seismologists were the biggest users of computer cycles. I think we've probably been overtaken by 12-year-old boys, but we're still a very heavy user of advanced computing methodologies and big computers. How do we acquire data in a marine environment? There are many ways. One of the most active ones is we use what's called a streamer. It's a long cable that's towed behind a ship, but it's not one long cable. It can be many, perhaps a dozen. The cables are long. They're several kilometers long these days. it's a tremendous engineering challenge to not only deploy these cables, but to steer a ship with GPS and to acquire data where you can position the sensor, or at least know the position of the sensor, to within a few meters, so you can adequately interpret the data. Ship can pull up to 100 kilometers of cable, not one cable, but multiple cables. Sensor spacing is on the order of a few meters. Often now we've gone to multiple ships, so we have not only one ship pulling both source and receivers or streamers, we have multiple ships, maybe 2 ships pulling sources and 2 ships pulling receivers. A lot of improvements in seismic sources. Usually we use air guns in the Gulf of Mexico, or multiple air guns that we try to tune to specific frequencies to try to get the maximum penetration of the Earth's subsurface. I didn't pick pictures from Schlumberger just because Brian's from Schlumberger, but these are some figures from some Schlumberger literature just showing a little bit about the evolution of how we've of data acquisition over the past few years. We used to acquire data similar to what's shown in the lower left, using one ship with several streamers and several air guns pulled behind the same ship. We now refer to that as narrow azimuth data. It had a fairly limited viewing angle of the Earth's subsurface, and it really restricted the kind of processing we could do, and that really limited the quality of images we got in the Earth's subsurface. With time, we decided that we would not just drive the ship east-west or in a set of parallel swaths across the target zone, but we drive them at different angles. This dramatically increased costs, but it also dramatically increased the quality of surveys. So we'd call that multi-azimuth. We used, again, one ship going at various angles crossing the region. With time, then we said, why not use multiple ships? That's the third set of figures. And in this figure, we're using 2 ships pulling large number of streamers, longer streamers, and multiple ships with air guns. Again, the idea is to increase penetration, to increase the angle with which we're viewing the Earth. And then we get the idea of rich azimuth, where we pull these ships, have these ships cross the region at multiple azimuths. More recently, Western GECO, a part of Schlumberger, has introduced the idea of coil shooting, where instead of pulling the ship in a set of parallel lines across a region, they've said, why not drive it in a circle? And this is, again, a tremendous navigational challenge, but they've shown some of the improvements in image quality we can get, particularly in subsalt regions, by doing this kind of survey that provides us a wide range of viewing angles. And this is just a figure from a recent paper published by someone from Schlumberger showing the major body there is that you see that's relatively homogeneous is salt, and the region that's circled in the left-hand image is the kind of image we got from a conventional survey, and the one on the right-hand side, the circle, is what we get by using a coil shooting survey. And the important thing here is that the oil reservoir butts up against the salt. And what we want to do is try to drill into that as close to the salt as possible, because the structures tend to tilt up dip to the salt. The fluid will migrate towards the salt. And so the closer to the salt we can put our wells, the more production you can get out of the well. And so the more return on investment you get from drilling that well. Other ways are used to try to improve the azimuth from which, or the viewing angle. There's been a lot of work in putting cables not only on or sensors not only on the surface, but we put them on the seafloor. For many years, several years, they've been putting cables on the seafloor, towing cables along the seafloor, sometimes just leaving cables on the seafloor so we can do repeat surveys. There's also been a lot of interest in putting seafloor nodes on to record 4-component data. That's 3 components of motion plus pressure on the seafloor. We use vertical seismic profiling. We put receivers in wells, and we shoot sources from the surface, so we get more vertical paths crossing through our region. This shows an example of a kind of vertical seismic profiling imaging we might do where we're looking at reflections from the below the array of receivers. We can do multiple source positions to try to get a wider range of angles. And again, we can also shoot a coil shooting into a vertical seismic profile. We also do cross-well shooting. If we have multiple wells, we can put sources in one well and receivers in another. So if we have these new acquisition approaches and new source methods, we'd like to try to benchmark our methods. How do we do that? It's hard to figure out how to get ground truth. Of course, the ground truth for an oil company is how much oil do you get. That involves the interplay between many disciplines, not just geophysics. But we'd like to think about how we can get ground truth. And one way we do that is through simulation. And that brings us to the project that we've been doing with multiple companies is to try to simulate something in the Earth's subsurface, a complex model in the Earth's subsurface that we can use to get benchmark data for testing our imaging algorithms. And this is a view of a model that we created to do massive simulation on, and a model that we try to make as complex as possible, including realistic reservoir structures, such as this turbidite, which is, again, something that has a lot of structure on various scales that's embedded in our model to try to make it more complicated for imaging. I'm going to skip that. This is just to show the imaging challenge. Such a project was done in the mid-90s. And this is to show where we are now. We're doing something that's on the order of 50,000 times more complicated, more computing cycles, at about 30% of the cost. The surprising thing about this simulation and about most work we do in oil and gas is that it's all based on the idea that the Earth is a fluid. We aren't considering anything to do with the solid part of the Earth, meaning the propagation of transverse waves. But also, surprisingly, most oil and gas has been found with that assumption. There's interest now in extending our ability to both simulate and image using the more realistic model that the Earth is a solid. It's really pushing our computational capability and our algorithm capabilities by looking at the solid aspects of the imaging, but there's a lot of work in that. Also interest in improved imaging algorithms. Traditionally, we've used finite difference simulations. There's more recent interest in integral formulation simulations that can more realistically model the Earth's complexity, such as rough interfaces. The upper simulation is a finite difference simulation that has a lot of numerical issues in it, and the lower one is a boundary integral method that greatly reduces the kind of numerical artifacts we get in our data. Beyond seismology, as I said, there's interest in electromagnetic methods. Just very briefly, to show that electromagnetic methods are often much more sensitive to fluids. Seismic methods tend to be relatively insensitive to the different kinds of fluids, whether they're brine or oil and gas. Resistivity tends to be much more sensitive. This is a series of, or the upper left hand is a sort of an X-ray through our model showing where the reservoirs are as a function of horizontal position. There's a region on the east side where that red region is the turbidite. That's a reservoir. The middle section on the upper side shows the resistivity of that turbidite and shows that the resistivity has an anomaly. And the bottom slides show that calculating the EM response of this region, there's actually something in the data that's responsive to these changes in resistivity associated with the presence of fluids. I just wanted to say very briefly that these methods are extensible to other regions. This is some work I'm doing in collaboration with folks in Iceland, looking at exploration for geothermal energy in a volcano in northern Iceland, where we're also doing things like combined geophysical imaging, combining seismic and magnetotelluric EM techniques to try to refine our images of subsurface to improve geothermal energy exploration. So in conclusion, we're doing a lot of work in not only improving acquisition, but improving methodology for processing data. I haven't touched on a lot of the processing methods. Doing full waveform inversion, where we adjust Earth parameters in a systematic way to try to reliably model the entire waveform that we observed, including the Earth's anisotropy, into models that give us improved images. Anisotropy due to geologic structures and that if we don't account for it, gives a mislocation of reservoirs. Joint imaging is important using seismic gravity EM methods. And I just wanted to say again, reiterating to all of you that this is combined worth from people in many disciplines of endeavor. So, thank you.